Hello, good afternoon. My name is Koirala. I am a professor of mathematics education in the education department here at Eastern. And I have been teaching at Eastern for the last 19 years. So I'm completing my term of department chair this August. And Marsha?
On the left hand, the left hand side.
I'm Dr. Marsha Davis.
Hello, I'm Marsha Davis. I'm department chair for the Department of Mathematics and Computer Science, and I have at least another year to go on my term as chair. So.
And we have been involved in teacher quality project for a long time. Marsha was already here when I came in 1995, and they had the TQP grant in 95. And we had the grant for many, many years. So many people have come and gone through our grants, different kind of grants. And this time, this is focused more on, as you know, science and mathematical modeling that fits into science, and that's what we are basically focusing on today.
We should just out of curiosity, do we have a split between math and science teachers? How many are math teachers? Oh, the minority, and the rest of your science?
Special ed.
Special ed? Administrators? For our own background.
So we have a really diverse group of people here with different experiences, but in the workshop, what we plan to do is talk about the Common Core Study Standards. This one probably you are familiar with, right? So in this diagram, you see the mathematics, M1, M2, and so on. Those are all mathematical practices, and we have 8 of them. And this diagram really does a nice job on how the mathematical practices fit into science and language arts, and especially that intersection in the middle. There is M3 and M4, construct viable arguments and critic reasoning of others. So basically they are expecting that people work in groups, they share information to each other, their findings, and then people evaluate each other so that the argument or their thought is stronger and more logical, and they become better. That is what is in the intersection. But almost like the number one there, make sense of problems and persevere in solving them. And that is very, very critical. Because what happens, we have 2 math teachers here. What happens in mathematics is the students give up too quickly. You know, if a problem sounds a little more difficult, they say, I'm done. I don't want to do it anymore. This is too difficult. They give up. And once they give up, they cannot be really mathematical problem solvers. Because for mathematical problem solving, people need to invest their time and energy. They need to keep on doing it. Perhaps you know what Einstein said. Einstein said that there is one difference between most of the people and myself. And he said, I just stay with the problem longer. And that makes a huge difference in mathematics learning. But perseverance is not something that you tell the students and then you tell them that you need to persevere, and they just persevere. I mean, it doesn't work like that. So we need to have problems that makes sense to them. So if there is something they find interesting, if they think that is relevant to them, to their everyday world, then it's more likely that they will persevere. And mathematical modeling in the context of science and language arts, that has more potential for students to develop that interest. So we think that mathematical modeling works pretty well with the science and language arts, and especially with science. But also, it is really critical that we look into the content, the grade level content, because the mathematical practices are supposed to be there every time. Whatever the grade level is, it doesn't matter. But then at the same time, there comes a list of content that our students need to learn. And this is like, you know this, but we put everything together just in one chart. Now, how many of you do the grade 6, 7, 8? So a few of you do grade 6, 7, 8. So the number system, expressions and equations, statistics and probability, ratios, and proportional relationship, functions, and geometry. So I think what we do in this presentation in the mathematical modeling workshop is focus more on statistics and probability. Actually, math modeling works with the number systems, with the expressions and equations. There are equations everywhere, but it's more related to statistics and probability in terms of the Common Core. And then when we go to the high school content, we have algebra, functions, and modeling. So there is modeling, and that's really what we are focusing on. And I think some statistics and probability, the kind of activities that we have and the data that we have, there is some statistics and probability in terms of content, but it's more like the modeling experience. And this is from the Common Core, directly copying from the Common Core. This is how they say the mathematical modeling. So you have a problem, you have to formulate the problem, compute, interpret the results, validate, and then we do the report writing or some solutions, and then use the interpretation also to formulate new problems. So this is from the Common Core, and Marsha has a 4-step process which is very similar to problem solving. And now, how many of you have heard about George Polya? George Polya is very famous in mathematics, and he is given a lot of well-deserved credits for developing theory of problem solving. And so according to Polya and other literature, mathematical problem solving is really at the heart of mathematics. And problem solving is not always easy. It is difficult, but it's very, very useful. It's real mathematics. And it demands, problem solving demands students that they analyze and synthesize different forms of mathematics. When you think about analysis and synthesis, like in the Bloom's taxonomy, where does it belong? Really at the high level, right? So analysis, synthesis, and evaluation. Those are higher order thinking. And that is what is required for mathematical problem solving. Charles and Lester are two other people who have done a lot of work on mathematical problem solving. And according to them, and it is pretty much accepted by mathematical community, that for a problem to become a problem, it has to have a mental block. So something could be a problem for me, but somebody else, that problem is not a problem anymore. So if it creates some kind of block for me, it is a problem. That is critical aspect of problem solving. And then the learner should have a desire to solve it. You see, that is a really hard thing to have if students are not interested in. So, and then if they have a desire to solve the problem, then they are more likely to put effort into that. So those three elements are very, very critical in mathematical problem solving. Just a note, sometimes like when there is an exercise from a math book, people say, oh, it's a problem, and we call that problem in everyday language. But from the problem solving perspective, that is not a problem. That is just a textbook exercise. So there is a difference between a problem and an exercise. And Polya's 4 steps. Step 1 is understanding the problem. So when students are trying to solve, like so many students actually cannot solve problems. They have no clue what to do because they are not understanding the problem. They don't know what is required, what is given, what is to be solved, and so on. But those are very critical aspects of problem solving. That is George Polya's 4 steps. And sometimes in some textbooks, Polya is given credit. But in some other textbooks, like there is the problem solving steps, You can actually see the 4 steps, but Polya is not given the credit that he deserves. Step 2 is devising a plan. So basically thinking about how to solve the problem, analyzing the problem, guessing, checking, drawing picture, making table, solving a smaller problem before they try to solve a bigger problem. Those are all the elements of devising a plan. Carry out the plan. This one is actually easier because all of the thinking goes in devising a plan. And sometimes like this could take different form. Some people who are really good, all of their plan is in their head and they can still carry out the problem. But for some people, they have to put everything on a piece of paper. They have to lay it down, put all of the steps. But that is a very, very important step. So once the problem is devised, basically carry out the plan is doing it what they designed. Step 4 is looking back. So looking back involves checking results, whether the answer, whether the results make sense, and if the problem could have been solved in an alternative way, and sometimes the alternative way could be a better way. So all of those things happen in looking back. Looking back is actually a very, very important step. Many people, they carry out the plan, they have the answer, and they say, I'm done. I already have the answer. And then perhaps you say, okay, can you look at if you notice something important? What do you mean? I'm done. I have the answer here.
Yeah, that's why I have to drive, 575 miles per hour down the highway, right?
So making sense of answers is very, very critical in mathematics, mathematical problem solving, and also mathematical modeling. And we have the mathematical modeling, a 4-step approach, which is not exactly the same thing as the 4-step problem solving, but there are some similar elements.
So I want to talk a little bit about mathematical modeling. And what I want to introduce is a model of mathematical modeling. And you'll understand why I'm calling this a model of mathematical modeling in a minute. But step 1 is to identify the situation, the problem to be investigated, the questions you need to ask or that you want to answer. There could be more than one question. So just sort of figuring out what is it that you need to know or what is it that you need to solve. That's step 1. In step 2, you start to make assumptions. You start to simplify the situation so you can actually make some mathematical sense out of it. Sometimes in the real world, things are just too complex that you can't account for absolutely everything that can happen. So you start to say, I think these factors are the most important, and these are factors that for now I'm going to ignore, and here are my assumptions about the factors that I think are important. And that those assumptions and the things you want to focus on should be the things that allow you to move forward with the mathematics to build a model. And now by building a model so that I can solve the model and answer my questions from step 1, it could be a formula, it could be some sort of table, it could be some sort of graphic display. I don't want you to think that it has to be 3x plus 5 equals 7. I'm going to solve for x type. It doesn't have to be that simple. But just some sort of way I'm going to set up the mathematics in such a way that I'm going to be able to use what I'm building based on the factors I'm using and the assumptions that I'm going to assume to be true, that I can build something that will allow me to answer the questions in step 1. But now this is the important part, and not unlike the looking back that we saw in problem solving. But at this point, I've come up with some sort of solution to the things I want to know or the questions I want to ask, and now I have to say, within the context of this problem, I have this mathematical solution, maybe this number, whatever. Does it make sense in the context that I started in? And in fact, how would I interpret that in the context that I want to know something about? And then you may find that you go, oh, maybe this isn't quite usable. Maybe you find that the length of something is between, with your model, between 3 and 10, and I need something that's more precise. And the only way I'm going to get that is to throw in a few more factors or a little more precision with my assumptions. And so this says, okay, either I like what I got for an answer, I think it's really usable, or it's totally wrong, or I need a little bit more precision, so I need to go back to step 2 and throw in another factor, change an assumption, and sort of cycle through and do the process all over again. So this is very different than what you'd see in a textbook, where a lot of times I say, oh, I do mathematical modeling, and people will say to me, oh, the application. Application doesn't usually have a loop. Mathematical modeling is a process. And so it's not really, you really need to be thinking about going through in a loop, maybe doing a first pass through of the most important things, throwing in the next phase where I'm going to throw in this little tweak to the assumption, go through it again, but the problem will be easier because I went through a first pass through. So not necessarily I'm going to follow one direct set of steps from beginning to end and get my answer. So that we do with textbook exercises, but not necessarily with math modeling. Sometimes we do, but not all the time. So now I'm going to give you an example of a mathematical model that was very near and dear to my heart. And it was actually at a time when I was working on a project called Mathematics Modeling Our World that was a high school series on mathematical modeling. I do a lot of work with COMAP, which is the Consortium of Mathematics and its Applications, but they're math modeling. That's basically what they do. And we were stuck in, I shouldn't say stuck, but I was stuck in Endicott College, and I live in Sturbridge, Massachusetts, and my daughter was in a play. She had a lead in the play, in a 6th grade play, and I was trying to get home. So I'm driving to get home, and I made the mistake of stopping at the rest stop just to get something to eat because I was famished. And the woman at the counter took longer than I had expected. And as I get into my car, I go, how am I going to make it in time for her performance? She had the first number. So in my head, I start doing this. I start saying, okay, what are the assumptions? It's now 6:55. I know that it's 5 miles from the rest stop to the toll booth, so I'm laying out my assumptions. I'm going to have to go through the toll booth because I didn't have speed pass at that time. It was before then. About 2 miles to get from my exit from the turnpike to the school, and there you're not going to be able to speed because there's going to be someone in front of you, 30 miles an hour. There are 2 stoplights. Well, I got to make an assumption. I'm going to miss one of them, so I'm going to, I mean, I could have said I'm going to make it through all. But I just thought, okay, I'll go halfway, figure that I'm going to hit one of them, lasts about 30 seconds. I'm going to be really late for this performance. If you know anything about 6th grade plays, I mean, everybody comes to those. I think it tapers off when you get to high school, but in elementary school, everybody comes, which meant I was parking way out and I was going to have to walk. So I figured 2 minutes. The play started at 7 o'clock, but you always give people 5 minutes, and then the principal has to get up there, and she's going to talk for 30 seconds. Okay, so I've set out all the different pieces, all the different assumptions. And now my question was, how fast would I have to drive on the highway in order to make it for the start of the performance? My daughter had the first number. So now I started to solve the problem. And usually we sort of think of problems, I'm actually going to solve this. I'm going to take this off for a minute because I can write on this board and then I can pull it down. So basically I started and I said, okay, I have 10.5 minutes to play around with. It's going to take me 2 minutes. Now I'm up to 8.5 minutes. And I'm going to lose 30 seconds. Okay, now I'm up to 8 minutes. And I'm doing this in my head while I'm like driving, getting ready to drive. So now I'm down to 8 minutes. 2 miles, 30 miles an hour, that's going to take me 4 minutes, so now I'm down to 4 minutes, 15 seconds, so I've got 3 3/4 minutes, and I've got to drive 5 miles in 3 3/4 minutes. And I go, okay, let's see, 3 3/4 minutes, that's 15 minutes. If I'm going to get to miles per hour, I have to convert that to hours, so that's going to be 1 hour, 60 minutes, and then that's going to be 15 over 240, and so hours, and I can see the 3 right in there, so I've got a 5 over 80, and I kind of left the 5 because I was doing this in my head, no calculators, I'm driving, you know, there's no hands-free calculator yet in the car. I'm sure it's coming. So this is hours, and now I'm driving 5 miles, 5 over 80 hours, and so I would have to drive 80 miles per hour. Now I've got to give you another piece of information. I live in Sturbridge. I don't know if you know anything about Sturbridge, Mass, but it has a state trooper's barrack. So there is always somebody on the road from the rest stop to the toll booth, and if I went 80 miles an hour, I was going to get stopped, and that would be another thing in my model, and I absolutely I was going to miss the first 15 minutes. So I couldn't go over 70, you know, that. So I just said, okay, resign yourself to the fact you're going to be late, and just drive your 70, because I think I can get by with that without the state trooper picking me up. And there's my solving of the model. Now, I get to test how good this was, because I was just making these up. There was nothing that said it was actually 5 miles from the, the rest stop to the toll booth. I knew this from experience. This is about how long it takes. I think it's about 5 miles. So all these things were coming from my own experience. So it wasn't just totally guess. I had some substance on which I could make a guess. But they weren't like given to me from a textbook. They were assumptions that I created. And what actually happened is I got into the school, and my daughter was in the first number, and no, I did not make the opening, but I was in my seat. She looked up as she finished her song, and I was there. And for all she knew, I'd been there the whole time. So it had a happy ending, but this may sound a little crazy, but after you get involved with mathematical modeling, you do things like this. And this was something that I actually did. But I wanted you to see it because I wanted you to think about the kinds of assumptions I was making and the fact that none of them were given, and they weren't for certain, but they weren't just outright total guesses. They had some foundation in my understanding of what the situation was. So that's an example of mathematical modeling.